Okay, well, thank you very much for this organization and the feel about the talks. I've been postponing this meeting for about 2 years, and you guys managed to pin me down at last, and I'm really glad that you managed to, because I'm very slippery. So today we'll be talking about how I think we could design organic intelligence to animate matter. So Josie had an amazing talk where he introduced many types of embodied intelligence. And one of the aspects I think a lot is about animation. When you see, even when you think about life, how you define life. And for me, in first instance, is something that moves, something that can achieve a task and that can move, at least. But not necessarily this can be alive. Of course, you have many other aspects. But nature decided that motion is one of the priorities if you need to reproduce and achieve other biological functions. Otherwise, you wouldn't be able to have cells, etc., coral reefs, and etc. So motion has always been like a central part of whatever nature is trying to do to achieve the biological function. So we start with this picture. It's a baby. And enormous complexity goes in there. I like also to bring these two other babies that are my two daughters, with 1.5 and 4.5 years old. And what you can see, these are ultrasounds. Ultrasounds when they were about probably less than 1 centimeter. And Josie talked about growth and body intelligence. My God, how much complexity is there in terms of everything, right? Life and everything, and also minuscule. And then you give time and the right ingredients, this grows and becomes a baby, becomes us. And if you're not fascinated by this, I don't know what is going to fascinate you. It's a mystery, isn't it? It's a mystery. And with the little time we have in this planet, what I'm trying to see is how can we understand a little bit about this process, also to understand from the sake of understanding, so the mechanistic understanding, but also to exploit this to build new things that we are not restricted by nature. If we think that what we create is not natural, it's artificial, we call it artificial. But if we are part of nature, what we create is also, of course, it should be natural. Anyway, a lot of philosophical discussions. But what I wanted to compare is with this little pepper here. Of course, it's very rigid. And you had to program every single interaction you need to get the response. And I don't need to convince you otherwise that this is not the future. This is definitely not the future. The future is something that is trying to mimic us as best as possible, as best as we can. But of course, if I start with a baby, or even me, it's too complicated. So being a mathematician, what I try to find is what is the atom of complexity? So you look at complexity. This is a picture of complexity. You see so many levels of complexity there. Where do you even start to look to get some understanding? Really difficult, isn't it? So you need to find the atom of complexity. So in this case, let's say from a forest, I'm getting a tree. Still, this is very complicated because you have so many length scales, so many time scales as well involved in this process. But whatever you do, then I try to mathematize this, rationalize this with a modeling framework in a way that can capture this fundamental aspect of what I want to describe. From these, I get some form of understanding, or at least I hope you understand something. Even if your model is wrong, it still is very important because it's giving you really precious ingredients on what is missing. So you are literally in a win-win situation because what you don't get right, it means that all your assumptions are weak and you should continue looking for this. So it's incredibly important, this process. You come with a mathematical recipe. What I mean by that is a mathematical model that you can make predictions and see what happens. And then once you have all these pieces of the puzzle, it's like a detective job. Then you come and say, okay, I'm ready to do some prototype and see how this actually works in real life. So I'll give you a few examples of this cycle and how we think about these different problems. So for example, the simple task of holding a cup. I don't need to convince you as well that we don't have to think really hard when you're holding a cup, right? Like, you just hold the cup. That's it. You can even forget that you're holding the cup. And if anything changes, you can still adapt. So there is a part of you, a part of your brain that is being devoted to that task. But also, there is a lot of, let's say, embodied intelligence here, in which this problem is being resolved between the cup and your hands. And that's why it's so difficult for us to code this in the robotic setting. You know, so many groups across the planet are trying to crack this problem. So when you go to the biology, for example, one of the key aspects is that we have muscles. Muscles are composed by a multi-scale structure. So we have here the muscle structure that goes in these cell bundles, that goes all the way to the myofibril, that goes all the way to the sarcomere. And this is a picture of the myofibril, bunch of filaments connected together in a beautiful geometrical fashion, very similar to the work that Josie presented before. Amazing. But hundreds of thousands of molecular motors are operating here. So is it fair for me to say that it's a simple problem? It's not. We have hundreds of thousands, millions of parts being combined so that we can resolve this problem without using our brain. So in a way, it's unfair that also the comparison with the robots, that they don't manage to do this, because of course we are not building this complexity. So where do we start? Again, I start here with the muscles, thinking, oh, maybe the muscles are my fundamental unit. It's not. Not, because you can tell it's very complicated. But then if you look more closely to other organisms, in particular microorganisms, they achieve this level of complexity with much simpler structures. So these are one of the early muscles, if you think, that they are in nature, but they are self-contained. You don't need, these are sperm cells, this is leishmania, this is chlamydomonas, this is sea-urchin sperm, this is paramelcium. All the unicellular organisms, they use muscles, but in a different form. We call these cilia or flagella. So what is wonderful about cilia and flagella is that these cells are stupid. They don't have a brain. They don't have even neurons. So we can't argue that they actually have any form of intelligence. That's out of the question. But what they do have is some kind of filamentous structure with motors, which are molecules that are doing the work in this otherwise passive structure. So this is for me the atom of embodied intelligence. If I manage to crack at this level, then I hope that I will be able to understand what happens if I add more complexity. So I'm trying to go to the simplest system that, of course, this is still very complex as I'm going to show you. The simplest system that you can gain information before you go deeper. And also, why not create something like this big if this was created at micro scale? So, and also exploit this phenomenon. So what I'm trying to sell you guys is the idea that cilia and flagella and unicellular organisms or cells, they are the building blocks of the embodied intelligence that we see in animals at much bigger scale, because you have all these structured layers and layers and layers. It would be impossible for us to model mathematically this, or even implement this as a robotic model. So let's see what happens. So because we are so interested in the structure, we need to talk a little bit about the structure. So this is just an example of a sperm cell. So you can think this is as a robot, but it really looks like an engineering structure. You have the genetic payload here and the cilium or flagellum. And the internal structure has an energy source, which is the mitochondria. You have these structures around here that we call all-dense fibers. But there are structures that tapers along the filament. Look how beautiful, which is also something that Josie was implementing in the elastically Bennett-Stephens variation, how important this is. Look here, nature exploiting this at the fundamental level of unicellular organisms. Absolutely beautiful. Then on the internal structure, you have these columns here. They have a name, but we call them axonym. They're beautiful symmetric columns, otherwise passive. These things you see here, these are the motors that propel this structure and deform this structure. We call them molecular motors. You give chemical energy, and then when you attach to a nearby filament, produce a shearing force, and then detach. Nobody knows how they work, and how they are organized, self-organized in hundreds of, thousands of that is still a big mystery, and which I absolutely adore about this problem as well, because even when I choose my fundamental unit, I can't fully understand. Anyway, so here is just an example that if you have two filaments and you try to shear across, they'll just slide. But this is this is intelligent material. They have cross-linkers, and these cross-linkers are there to transform tangential motion into bending motion. Forces that are tangential into forces that are normal, perpendicular to the structure. So what I see here is a robot. We could make this big, small, because these underlying ideas are already there in continuum robotics, etc., etc. But there is more to here than what we can review by just looking at what we create. Now, these are human sperm cells swimming in a fluid. And now I want you to imagine everything I just told you. In this filament that you cannot see inside, you have hundreds of thousands of these molecular motors. They're deciding what to do and how to bend in a way that you can send these traveling waves. They can sense the environment, they can change direction, they can find the egg, they can find places where you have more viscosity, etc., etc. Very complicated tasks at the unicellular level. So how does this work? How does embodied intelligence work? And can we build something with these ingredients as well? There is a tiny problem. This structure here is very different from just an elastic rod, isn't it? If you see from the outside, everybody until now would just look at this and say, oh, this is just a filament that is bending. Just a filament that is bending. And then you cross-grain or you forget the fact that you have all these columns together. But if you do this, something really bad happens. Because some people decide to do an experiment where they kill the sperm and they just bend this structure. And what they found, when you bend, so this head is stuck in the substrate, and this is a micropipette tip that you try to bend the structure. And what you find is that it bends in the opposite direction, in a section that shouldn't be doing anything, because there's no forces there, there's no motors. And that was fascinating. That was called paradoxical phenomenon. Paradoxical because nobody could understand. A structure that when you bend, then it counterbends in the other direction at the micro scale. And then people thought, because this is rat sperm, and rat sperm has a lot of additional structure, maybe it's because of that. Let's go to a simpler organism. Same group did the same experiments with sea urchin sperm that only have the axoneme structure. And again, they found that if you bend the flagellum, it bends in the opposite direction. So clearly, our view that this is just an elastic filament is wrong. There's something wrong. There's some other intelligence there that we're missing. And if you solve the elastic problem, this is exactly what you find. So this is me solving this problem. You put a force in here in the middle. And what you find, if this is just a regular passive structure, this is going to be, this section that is not being forced is going to be straight, of course. So what is missing? Well, what is missing is the cross-linking. So this cross-linking is more important than we ever thought. Because some equations, when you put this cross-linking back, look, you get the counterband back. And what this cross-linking is showing is that sliding of here is coupled non-locally in the structure. What is happening here, what is happening here is coupled non-locally with what is happening here. What that means is that this is an intelligent structure. If I have molecular motors stressing this part, this is already communicating with motors really find the structure. Look how beautiful this is. So that they can self-organize, synchronize, and send these beautiful traveling waves. So one part of the answer is in the structure. And combining, like, sorry, Jose, I'm using a lot your talk because it had so many interesting aspects, like the previous talk. And how can we engineer interactions in such a way that we build intelligence or high intelligence, especially non-local intelligence? Most of the structures we create, they are locally interacting only. And what biology is saying that yes, this is cool. You can do a lot of this, but imagine if you couple them non-locally. It means that if I'm having information here, already sharing with you, verifying the back with no time delays, instantaneous in time, which is critical if you want to survive, right? Nature is incredibly clever. So here's some equations again, and that we can basically recover what they saw in the experiment. So our job in this particular section was to show that this phenomenon is not paradoxical. That was just an ingredient that was missing, and this ingredient was the coupling between different structures, even though they are very tiny and at the molecular level. So what we can do with this kind of techniques? So, for example, in here, what we find is that this is in motion. So you have the structure that I mentioned, that is an intelligent structure, plus molecular motor is going to give you some kind of adaptive animation. And let's say we don't know now, so we cover this, the structure, but now we don't know how intelligent the activity is. So you can do experiments, and you can, because all the forces and all the torques are balanced in this equation here. This means that you can invert the equation and actually measure what the molecular motors, what the activity is doing. So basically what I'm measuring here is what this primitive muscle is doing. And then what we find which is not a big surprise, is a traveling wave of contraction that is happening there. Fantastic. Traveling waves are stripes in space-time. So this is a wave that is going along the flagellum, traveling across, and these are waves of curvature. Yeah. So it looks like that different parts of the flagellum are working as as a rowing boat, or you can also think as different pendulums, in which each section you have a different oscillator. These oscillators, like pendulums, they are imparting force to the system, but they're not in isolation. They're coupled. They're coupled to nearby segments, but also coupled non-locally too. And the result of that is this beautiful traveling wave that doesn't matter what happens, they always generate a robust traveling wave. But what I wanted to draw your attention is that these, like, if you really bend your imagination, these are stripes as well. I'm not trying to say that zebra stripes are the same as the space-time stripes, but maybe I am. And let me try to convince you why. Maybe you know or have heard of famous mathematician, Alan Turing. Got even more famous after the imitation game, and very important during the World War for being crucial in breaking the Enigma code. But actually, he's more famous among mathematicians because he discovered a new type of instability that we call Turing instability. And we also call this Turing patterns. What Turing discovered was that if you have diffusion of molecules, also react to themselves. So motion and reaction leads to patterns in visual patterns, like spots, like stripes, like spirals and things like that. And he proposed that maybe this is what is happening behind the scenes in many of the patterns we see in biology, including, for example, fish, zebra stripes, even the fact that we have 5 fingers during embryogenesis is a pattern as well. You can have other solutions, which is like 7 fingers or 3 fingers, but they are not robust. So it doesn't come very often. So even the fact that you have one head as well is a pattern that emerges. And emerged when chemicals are negotiating at the very fundamental level during embryogenesis or morphogenesis, the genesis of morph. Yeah? So, to cut this story short, what we discovered is that a very similar system is underplaying in the motion of cilium flagella. We discovered that the molecular motors are working as a reaction system, as a chemical reaction system, because they bind and they unbind through chemical reactions. But diffusion is not coming because the molecules are diffusing, but because the structure provides diffusion of bending, diffusion of deformation. So we're talking about a completely different idea, not of molecules in. And then, like Turing, if I put reaction plus diffusion, I get a pattern. In this particular case, a pattern in space-time, which is stripe. So stripes in space-time are bending waves. So then, this is the result. You can see what happens. And we also match this with experiments. And these are cilia and flagella for different microorganisms. But what is the important learning here is that we didn't need to add the complicated fluid mechanics around or the environment. And also it looks like that these organisms don't even know that there is a fluid around, because they will generate this pattern regardless of what is outside. They will be able to adapt to outside, but they don't need to know what is outside, which is absolutely crazy, at least for all the aquatic species that are working in a low viscosity medium or like aqueous medium. Sorry, I realize this is a lot of things to unpack, but the message here is that the building blocks of, it looks like that the building blocks of intelligence for these microorganisms are some form of diffusion. In this case, we have no local diffusion because of what I mentioned about the sliding. There's more clever diffusion, it's not just local diffusion. And this diffusion I'm talking about is not the diffusion of moving molecules, it's the diffusion of deformation. If I could deform an elastic, imagine here I'm deforming an elastic filament. If I release this filament will try to unbend and go to a straight configuration. And this unbending is basically the diffusion of this deformation to the straight configuration. In the same way, the physics, the mathematics is the same, the physics is different. In the same way that if you put a droplet of dye in water, this dye is going to diffuse and equilibrate into the whole. These two processes are physically very distant. Mathematically, they are identical because they are governed by a diffusion type of. So this is also where mathematics helps us to see really distant connections, things that we never thought that would be connected, see, because the mathematical is the same. So now we know that we can use morphochemistry with diffusion, but that's complicated still. It's helping us to unveil and understand a lot of what is happening at the biological and biophysical level. But if I want to make a robot with real molecular motors, that's going to be complicated. I just wanted to draw your attention that it's not the first time. So this is like a myosin walking in an actin filament. And this is cell division as well. Again, molecular motors in filaments seems to be the two building blocks that nature uses in different configurations, in different morphology to achieve high levels of function in the system. So, as I mentioned before, it is difficult to make this artificially. So we ask another question. So going back to the muscle, what we know is that, again, molecular motors in muscles, they attach and then detach to nearby filaments to drive muscle contraction or to drive the cilia contraction, the more primitive cilia. But now the question is, can we relax the fact they are chemical species? Can we make them mechanical? Can we make them artificial? Can we make them electric motors? Can we completely replace a molecular motor by something that has nothing to do with molecules and stick there an electric motor? And completely replace all these molecular motors by rotors that instead of having this binding and unbinding rate in this way, they will rotate, and whenever they find a tooth, they bind, and they exert force. If they don't find a tooth, then they don't bind. So the binding kinetics is related, is more dependent on where you have a motor into. What is critical though here is that we put this abstraction, both mathematical and robotic abstraction, into a geometry that is similar to what you would find in the real muscle, the sarcomere. Don't worry, just big names. A muscle unit, a small muscle unit. Yeah? And what we found is amazing. Because anyone can argue that this is a very low budget robotic model. They synchronize, they self-organize in traveling waves. And they display a level of complexity that is parallel with real muscles. Look here, this is a myofibril in the micro scale that people put needles and they measure the deformation. So this is at the micro scale experiments and how they self-organize into this very nice oscillatory behavior that has this up, flat, and then coming down. People have been trying to capture this picture for the past 30 years from the biophysics perspective alone. But our motivation was like, can we just get something similar? And this is what you get. And this is what you get from the system. Very similar behavior, extreme levels of adaptability, and also similar traveling waves. So what this is showing us for the first time ever is that, yes, nature is great. There is a level of complexity there that they can do potentially better things if they are chemical motors. But if we replace them by our stupid motors, in the similar structure, we have similar level of intelligence. So for me, this is my muscle unit now, that then I will be able to build on top of that and get more complexity. This is my sarcomere. But big. That's opening up so many questions, so many cool things. So I don't know how much time I have, but I'll just change gears very quickly, because this is an example where we could make the robotic model, but also there are moments where the complexity is too high, and we need even to make mathematical modeling. So we created a kind of a sub-robotic multi-physics solver that can cope with all sorts of physics, multi-physics, and interactions. And you can see here, for example, filaments swimming, for example, this guy swimming, filaments interacting with fluids, and a bunch of filaments or systems kind of self-interacting to generate active animation. All these without me, everything here is self-organized. Okay? I'm not adding any kinematic constraint, nothing. You put the parameters and you get the results. The system decides what's going to be. So we call this self-organization. So to give you a glance of what it looks like, something that is really complicated, where we actually model all the filaments, all the motors, all together to see what kind of adaptation you get. And what you find is something astonishing. For example, in this case, when you have helical waves that travels along and propels these forward. But if you add something that you see in biology, which is, you can see here, but there is a bridge between two structures. That is a much stiffer bridge than the other bridges. And then you have the complete collapse of the traveling waves to the plane. So something that is inherently three-dimensional becomes two-dimensional just because of a molecular bridge that you put. Another level of self-organization adaptation. And guess what? This bridge is what you find in most of organisms that have clonability. So at the same time that this gives a level of adaptation, also is showing how the system is subject to small changes in the environment. I'm going to pass through this and just show that we also expanding to other areas. For example, try to do the same, but at the micro scale. So these are examples of ciliary flow that we're doing at the micro scale, using this time other type of actuation, acoustic, using sound for that. And I have many, many other examples. I'm running out of time, so I better go. I'll just stop here with my two daughters and say thank you, obrigado, everyone. Yeah, and get in touch if you want to bounce ideas. And yeah, thank you again for inviting. Sorry, it's been so long.
That's fine.